Welcome everyone to another episode of Mike Talks AI. I'm Mike, your host. And wow, do we have an exciting lineup today. We're diving deep into neural networks. Joining us is Alice, a data science enthusiast who's super passionate about transformer models. Alice, welcome.
Hey Mike, thanks so much. I'm seriously thrilled to be here. Neural networks are just, well, fascinating stuff.
Also with us is Christy, an AI researcher who's always exploring the cutting edge in machine learning. Christy, great to have you.
Hey there, pleasure to join, Mike. I always love chatting about AI, especially the fun, nerdy bits.
And finally, we've got Melanie with us. She's a neural network engineer who's done some incredible work in anomaly detection. Melanie, how's it going?
Hi Mike, super excited to be here. Can't wait to dig in.
All right, let's kick things off. Alice, for those tuning in who might be new to this, what is a neural network and why should we care?
Great question. So neural networks help us make predictions and automate tough decisions, like flagging security anomalies or helping cars avoid obstacles. Honestly, traditional code just doesn't cut it anymore.
Wait, so you're saying we can't just throw in a bunch of, if else, statements and call it a day?
Haha, exactly, Christy. Trying to manually code for every possible outcome, that's just not scalable. Neural networks find the patterns for us.
Melanie, I'd love your take. Could you walk us through the basic parts of a neural network?
Sure thing. So imagine tiny decision units called neurons, right? They're grouped into layers. Input, hidden, and output. Each neuron takes inputs, applies weights, runs them through an activation function, and voila, an output.
Nice, so there's a learning process in play. Alice, how does a neural network actually get smarter over time?
That's where backpropagation kicks in. It's like the network learning from its mistakes. It tweaks the weights to reduce errors. Although not all networks do that, some like feed-forward ones just, well, move forward.
Interesting. Melanie, I hear people say more layers equal better results. Is that true?
Honestly, not always. More layers add complexity, sure, but only if they actually improve learning. It's a bit of science, a bit of gut feeling.
Christy, you asked about real-world stuff. Alice, do you have a use case you've worked on?
Oh yeah, I worked on classifying network packets, normal versus abnormal. My first try, total disaster, 49% accuracy. I was like, yikes.
Ouch, so what did you change?
I shifted to using an autoencoder. It learned what normal looked like and flagged anything weird as abnormal. Once I cleaned and normalized the data properly, accuracy jumped to over 96%.
Whoa, that's a huge leap. But were those outliers actual intrusions?
Good question, not necessarily. They were just, well, whether they're malicious, that's a whole other level of analysis.
Final thoughts for listeners trying to build their first neural network.
Totally start small. Grab a clean dataset off Kaggle, know what you're trying to achieve, and prep your data like your model depends on it, because it does. And hey, I keep notes on L1, L2, backprop all stuck to my wall, it helps.
All right, that was such a cool dive into anomaly detection, but let's shift gears a bit. I want to take us from what went wrong on the network to what did someone think of that wireless speaker they just bought. In other words, let's talk about using neural networks to rate user reviews.
Ooh yes, sentiment and review ratings are such an underrated application of neural networks. I mean, think about it, we rely on product ratings all the time to make decisions. Should I buy this blender? Is this book any good? And when a model can help us predict those ratings from just the review text, that's powerful.
Right, and it's not just about giving stars. It's about helping platforms surface better content, giving visibility to genuinely helpful reviews, and filtering out junk. Also, I've always found it kind of fascinating how we go from messy, emotional human language to something a machine can score from 1 to 5.
Exactly. That's where things get super interesting. Because remember, machines don't feel the review. They see it as raw text. So the first step is translating that text into numbers. And for that, we use something like TF-IDF, which basically tells the model which words matter most in a review.
Right, so instead of reading the review like a human would, the neural network sees a matrix, rows and columns of word weights, and it learns to associate certain patterns of words with ratings.
Yup, and once you've prepped your data, you feed it into something like an MLP regressor. It's like a cousin to the classification models we've used, but instead of saying this is spam or not spam, it learns to predict a score like 4.3 stars, which is a regression task, not classification.
I'm curious. How do we know it's doing well, though? Like, sure, it spits out a number, but how do we know if it's a good number?
Good question. That's where loss functions and evaluation metrics come in. You track how close the model's predicted ratings are to the actual ones. If your model consistently predicts threes for things that were really 5-star reviews, the loss is going to stay high. And if you plot the loss over time, over what we call epochs, you'll see whether the model's improving or just stuck.
And if the loss drops at first but then suddenly spikes or plateaus, that's usually a red flag, right? Like, maybe the learning rate's off or the model's starting to overfit.
Totally, overfitting is like when your model becomes that student who memorizes the textbook instead of understanding the material. It does great on the training data, but when you show it a new review, it's lost. That's why we split data into training and testing sets to check if the model can generalize.
I love that analogy, Alice. So when we say the model's overfitting, we often see it too, like a training score that's great but validation score. Yikes.
Exactly. You might literally see it in graphs, training loss going down, but validation loss creeping up. That's our visual cue that the model's not really learning the deeper patterns, it's just memorizing.
And speaking of visuals, Melanie, I saw in your last project you actually visualized the weights and biases in your neural network.
Yeah, it's super helpful. Think of weights like the volume knobs on each input. How much should this word matter? Visualizing those gives you insight into what the model thinks is important. If you see one input dominating everything, might be a red flag, or maybe a feature to investigate.
And biases are like offsets, right? Kind of like a default setting the neuron starts with before the inputs nudge it around. Visualizing those can tell you how your model is primed to think even before it sees the actual data.
I never thought about biases that way, but that's a neat metaphor. It's like emotional bias, what the model assumes before you say anything.
So putting this all together, you clean the data, vectorize the text, split it, feed it to an MLP regressor, monitor loss, watch for overfitting, maybe visualize the internals. And boom, a model that can read a review and give it a rating.
Pretty much, and the beauty is, once it's trained, you can drop in new reviews and get instant scores. That's powerful for platforms that deal with thousands of new reviews every day.
But don't forget, it's not just about building the model, it's about making it useful. So choose your loss function carefully, keep your data clean, and always validate. That's how you go from toy project to production grade tool.
Beautifully said. All right, coming up next, we'll unpack how these models could predict customer churn using deep learning. But first, a quick break. Welcome back to Mike Talks AI. I'm Mike, and if you thought review scoring with neural networks was cool, just wait. We're now jumping into a whole new territory, predicting customer churn using deep learning.
Ooh, churn prediction, that's such a mission-critical use case. Like if your business can spot who's about to leave, you can actually do something about it before it's too late.
Totally. Because every retained customer is more than just a saved account. It's saved revenue, reduced acquisition costs, and honestly, stronger brand loyalty.
Exactly. And today we're building a churn prediction model using a convolutional neural network. Yes, you heard that right. CNNs. Usually for image data, but we're going to reshape structured tabular data and use conv 1D layers to pull out patterns.
Whoa, so you're saying we're taking numeric customer data, like tenure, monthly charges, service history, and treating it like a sequence. I love it. Creative reuse of CNNs.
Yep, but before we even get to the model, there's some hardcore data prep that needs to happen. First off, converting numeric columns like tenure and monthly charges into actual numeric types and filling in missing values using simple imputer with a mean strategy.
Right, because neural nets don't like messy data. They expect everything clean, scaled, and ready to crunch.
We also toss out duplicate rows. Those can seriously skew our model's understanding of real customer behavior. And after that, feature scaling. Gotta get all your variables on the same scale so no one's overpowering the others.
I imagine there's some encoding magic happening too, right? Those categorical variables like internet service and contract, they don't mean anything to a machine unless we translate them.
Bingo, one hot encoding for the win. Every category becomes its own column. So now the model can learn patterns like fiber optic users with month-to-month contracts are more likely to churn.
What about the target variable, that churn column? How do we handle that?
We encode it to ones and zeros, 1 for churn, 0 for not churn. And we must check for missing values in that column. If there are empty values, we drop those rows, otherwise the model would be flying blind.
Nice, and I'm guessing there's some resampling going on too. Since not everyone churns, the dataset's probably imbalanced.
Exactly. We use SMOTE, synthetic minority oversampling technique. It generates synthetic examples of the minority class, so the model doesn't just default to saying, no churn all the time.
Let's talk feature engineering though. I love this part, getting clever with new insights. I heard you created an interaction feature between tenure and monthly charges.
Yeah, we multiply them. So if someone has been around a long time but pays a lot, or a short time and pays little, those different dynamics get captured. And we also generate polynomial features to tease out nonlinear relationships.
Okay, let's get to the juicy part. You said CNNs. How do we go from tabular data to convolutional layers?
First, we reshape our input so it has that sequence, structure, basically a 1D array per customer. Then we stack two conv 1D and max pooling 1D layers. These help learn local patterns in the data, like clusters of behaviors that might signal churn.
Then comes the flatten layer, transforming that 1D filter output into something we can pass into our dense layers, right?
Yup, then we hit it with 3 dense layers. These are the model's decision-making core. Dropout is in there too, to keep it from overfitting. And finally, a single neuron with a sigmoid activation gives us a churn probability.
And boom, we've got a model that doesn't just say who left, but who's about to leave. That's predictive power in action.
And don't forget, we train it using fit on our training set, validate on our holdout data, and then we can feed it brand new customers and get instant risk scores.
This is seriously next level. From raw Excel sheets to a working churn prediction model, powered by convolutional layers no less.
Right, and that's just one domain. But buckle up because now we're shifting gears from predicting churn with CNNs to something that's redefined how machines understand language. I'm talking about transformers. Let's get into it. Okay, so we've gone to transformers, which literally changed the game in NLP. Welcome back to the podcast, everyone. I'm Mike, and today we're stepping into some seriously groundbreaking stuff. Melanie, what do you think?
Yeah, welcome back. So, Mike, transformers are kind of like the moment you realize you don't need to read a book line by line to get the big picture. You just look at the whole thing at once. That's what attention does. It's like, hey, every word, pay attention to everything else all at once.
Exactly, and this came from the now legendary paper, Attention is All You Need. No convolutions, no recurrence, just pure attention. It's like saying, let's toss out tradition and see what happens, and what happened? Magic.
It's wild because each word gets turned into a vector, right? That's the embedding. But transformers don't just stop there. They add positional encoding so the model knows where the word is in the sentence. Otherwise, I love you and you love I would look the same.
That blew my mind. It's like giving every word a little GPS tag. And then comes multi-head attention. So instead of looking at relationships in just one way, it opens multiple attention channels, like analyzing tone, grammar, and structure all at once.
Right, and each attention head might pick up something different. One could focus on subjects, another on objects, another on mood. Then it combines all that insight. That's what makes it so powerful. It's not guessing, it's analyzing everything simultaneously.
And the way they structure the layers is elegant. After attention, you've got normalization to stabilize learning, then a feed-forward network to crunch those rich attention outputs, and boom, you're building meaning.
We should remind listeners, this isn't just theory. We actually implemented a transformer trained to mimic the dialogue style of the show Friends. Took all 61,310 utterances. Shout out to those who still love Excel, 'cause that's where it started.
Yes, and you embedded every token, passed it through a stack of transformer layers built with PyTorch. But let's be real, the CPU version took days. You had to bring in the GPU cavalry just to make it manageable.
Kaggle's P100 saved us, from 2 hours per epic down to something usable, and that's the thing, these models are beasts. You need the right tools to train them well, otherwise you're burning time like a candle at both ends. And let's not forget about inference. Once trained, we can load it up, pass in a sentence like "how you doin'," and if the model saw enough of Joey, it might actually respond like him. We're not just predicting text, we're recreating character style.
But if it's never seen a word, game over. Transformers only work with what they've seen during training. So if Snargleblatz wasn't in the Friends script, don't expect a clever comeback.
We're basically giving machines language intuition. That's the dream, right? And the fact that the same architecture can handle image generation, speech recognition, and even medical imaging. That's Transformers flexing on the world.
And remember, hyperparameter tuning matters big time. Learning rate, number of layers, attention heads. Change the wrong one and your model goes from Shakespeare to gibberish. Or worse, and errors during training.
So yeah, to everyone listening, Transformers aren't just hype. They're the engine behind ChatGPT doll EBERT GPT-3. Name a modern AI marvel, it probably has attention mechanisms at its core. And we're just scratching the surface. It's kind of alarming how good it is.
Okay, so stepping out of language for a sec, what if we use deep learning to understand something physical? Like how people actually move through a retail space.
Wait, are we talking like smart store layouts? Predictive path planning?
Exactly. Picture this. Customers walking through a store, and we're capturing that movement as time series data. Now, enter LSTMs, long short-term memory networks. They're built for this kind of thing.
Right, because LSTMs hold on to what happened earlier in the sequence. Perfect for understanding, say, if someone just passed the snacks aisle, are they likely heading for beverages next?
Yes, you basically map the store to a grid, and each movement becomes a step in a sequence. So your input to the LSTM is like 200 steps of movement history per customer.
That's kind of brilliant. You're treating physical location like language tokens, am I correct?
Yeah, and instead of predicting the next word, we predict the next location. The output, two numbers, X and Y coordinates on that store grid.
Hold on, how do you train that? Like, what does the model even see?
So you've got X, your input sequences, and Y, the target next positions. Everything's scaled between 0 and 1 with min-max scaler. The LSTM layers digest that sequence and spit out predicted coordinates. The model is trained with MAE and MSE to measure accuracy and stability.
True, and MAE is easy to interpret. If it's low, you're saying, hey, I can guess where this person's heading with decent precision.
Exactly. And here's the kicker. The model learns nonlinear movement patterns. Like if someone loops back after skipping an aisle, a simple Python script would never catch that nuance, but the LSTM might.
Oh, and did you use gradient clipping? Because if not, LSTMs can freak out during training.
Yup, Atom Optimizer with clipvalue equals 1 to keep those gradients in check. Without that, it's chaotic city.
Okay, but real talk, what's the output look like? Like, how accurate are we talking?
Here's an example. Actual position was 0, 80, 0.74, but predicted was around 0, 51, 0.49. So we're not dead on, but the model's hovering close to the right zone, enough to drive decisions like layout tweaks or targeted offers.
And over time, the model learns patterns, right? Like if people usually move toward dairy after bread, boom, that's leverage.
Exactly. You can predict traffic bottlenecks, optimize staff placement, even launch micro-campaigns mid-aisle. It's actionable intelligence, not just analytics.
Honestly, it's wild. We started with CNNs for churn, dove into transformers for text, and now we're literally predicting real-world movement with LSTMs. Deep learning's not just software, it's spatial strategy now.
And with every step they take, customers are training your model to serve them better.
Yeah, this is the future of retail. Invisible AI shaping how we shop without anyone realizing it. So welcome back to the show, everyone. No, we're going to dive into how reinforcement learning can literally make traffic jams a thing of the past. Alice, Christy, Melanie, you ready?
Oh, totally. Mike, can I just start by saying, the roots of RL are way older than most people think. Like 1948 old. There was this wild pain and pleasure hardware system that literally erased its memory if it got a pain signal. If it got a pleasure stimulus, it kept the memory. That's basically trial and error learning in a box.
Wait, Christy, you mean they were doing RL before computers were even a thing?
Exactly, Alice. And even before that, Pavlov, yes, the dog guy was laying the groundwork. His research on conditioned reflexes, that's where the term reinforcement learning comes from. He showed that animals, and by extension machines, can learn associations between actions and rewards.
Right, and that's super important for RL because it's all about learning from feedback. If the agent does something good, it gets a reward. If not, it gets a punishment. Over time, it learns which actions give the best rewards.
But hold on, there's also a mathematical side to this, right? Like, we're not just copying animal brains. There's this whole thing called optimal control from the 1950s. That's where the Bellman equation comes in. It's a way to mathematically figure out the best move at every step.
Yes, the Bellman equation is basically the backbone of RL. It tells you how to update your strategy based on what you just learned. And that's where Markov decision processes, MDPs, come in. They model situations where you have randomness and control, like traffic lights.
Let me jump in here. MDPs have four main parts: states, actions, transition probabilities, and rewards. So, in our traffic light example, the state could be the number of cars waiting, the action is which light turns green, the transition is how traffic changes, and the reward is, say, negative waiting time.
Exactly, Melanie, and the agent, our traffic light controller, tries to learn a policy. That's just a fancy word for a strategy. If I see this many cars, I should do this. The goal, maximize the total reward, or in our case, minimize the total waiting time.
So, to make this concrete, at each time step, the agent looks at the current state like how many cars are waiting, picks an action, which light to turn green, and gets a reward like minus the total waiting time. The environment then updates, maybe more cars arrive, maybe the queue shrinks, and the agent repeats.
And what's cool is that our code actually implements this using deep queue networks, or DQNs. That's a type of RL algorithm that uses a neural network to estimate the value of taking certain actions in certain states.
Oh, and DQNs are based on Q-learning, which was invented by Chris Watkins in 1989. He figured out how to teach agents to learn the value of actions even when rewards are delayed. Like, you might only know you made a good traffic decision 5 minutes later.
But Alice, can you explain how the neural network fits in? Like, why not just use a big table?
Great question. In simple cases, you could use a table called a Q-table to store the value of every state action pair. But with something like traffic, the number of possible states is huge. So we use a neural network to approximate the Q values instead.
And here, where it gets technical but awesome. Our DQN uses something called experience replay. Instead of learning from just the most recent experience, it stores a bunch of past experiences in a memory buffer. During training, it randomly samples from this buffer. That way, the learning isn't biased by recent events.
Let me add, this helps break the correlation between consecutive experiences. If you only learned from what just happened, your model might get stuck in a rut. Experience replay makes the learning more stable.
And there's another trick called fixed Q targets. We use a second, slower updating neural network to calculate the target Q values. This keeps the training stable, so the model doesn't chase a moving target every time it updates.
Wait, so how does the agent actually pick actions? Is it always greedy?
Nope, we use an epsilon greedy strategy. At first, the agent picks random actions, a lot. This is called exploration. Over time, it starts picking the best known action more often, exploitation. Epsilon starts high and decays over time.
So in the beginning, the traffic light might make some weird choices, but as it learns, it gets smarter and smarter about which direction to let through.
Exactly, and that's how it discovers strategies that a human might never think of. Like, maybe letting a small side street go green for just a second at the right time can clear a jam before it happens.
Can I jump in with some RL history? There are a ton of algorithms out there: A to C, ACER, DDPG, PPO, TRPO, and more. Each has its own strengths. For traffic lights, DQN is popular because it works well with discrete actions, but if you had continuous control, like adjusting the length of the green light, you might use DDPG or PPO.
And don't forget about GAIL and her. GAIL lets you imitate expert behavior, while her helps when rewards are really rare, like if you only get a reward when there are 0 cars waiting.
But our code sticks to DQN, which is great for beginners. You have a neural network, a replay buffer, and an epsilon greedy policy. The agent learns by updating its Q values using the Bellman equation.
Right, and in terms of code, you'd see something like, for each step, store state, action, reward, next state done in the replay memory. Then sample a batch, calculate the target Q values, and update the neural network.
And every so often, copy the main network's weights to the target network. That's the fixed Q target trick.
One thing I love is how this all ties back to animal learning. The agent is basically like a rat in a maze, trying different paths and learning which ones lead to cheese, or, in our case, less traffic.
But it's not just about traffic. RL and MDPs are used in robotics, economics, manufacturing, even game playing. Remember Samuel's checker playing program? That used value iteration to get better at checkers.
And there are different modes of control. Some agents just react to the current state, primitive mode, while others try to predict the future, look-ahead control. Our code is more primitive. It doesn't simulate future actions, just reacts to what's happening now.
But you could totally extend it. If you wanted to, you could add a model of the environment and do model-based RL, where the agent learns the rules of traffic and predicts what will happen next.
And as RL gets more advanced, we can even imagine hybrid agents that switch between strategies depending on the situation. Like maybe it uses look-ahead control during rush hour but primitive control late at night.
The possibilities are endless. And the best part is you don't need to be a math genius to get started. If you understand the basics, states, actions, rewards, and how to update your Q values, you can build your own RL agent.
So to wrap up, RL is inspired by psychology, grounded in math, and powered by neural networks. It's how we can teach machines to optimize traffic, play games, or even run factories, all by learning from experience.
And with tools like DQN, beginners can jump right in. Just remember, it's all about trial and error, learning from feedback, and always striving for that optimal policy.
Couldn't have said it better myself. Thanks everyone for making RL sound so fun and approachable. Next time you're stuck at a red light, just remember somewhere an AI agent is learning to make your commute smoother. All right, everyone, let's switch gears. We've talked about reinforcement learning, but let's discuss transfer learning, how we can make models smarter by borrowing knowledge from one task to help with another. Alice, Christy, Melanie, are you ready to unpack this?
Oh, absolutely, Mike. And can I just say, transfer learning is one of those ideas that feels like it's always been around, but it's actually got deep roots in psychology, not just machine learning. Like, people have been studying how we transfer skills and knowledge for over a century.
Wait, Alice, are you saying transfer learning isn't just a machine learning thing? That's wild.
Exactly, Christy. The whole idea comes from educational psychology. Back in the early 1900s, researchers like Thorndike and Woodworth were already asking, if you get good at one thing, does it help you get good at something else? Turns out, it depends on how similar the tasks are.
So, if you learn to play the violin, you might pick up the piano faster because both are musical instruments. That makes sense.
Right, Melanie? That's a classic example of positive transfer. But here, where it gets tricky. Sometimes previous experience can actually make it harder to learn something new. That's called negative transfer. Like, if you know Spanish, you might mix up words when learning French, even though they're both Romance languages.
Whoa, negative transfer? I never thought about that. So in machine learning, does that mean a model trained on cats and dogs might mess up if you try to use it for cars and trucks?
Great point, Christy. In machine learning, negative transfer happens when the knowledge from the source domain actually hurts performance on the target domain. If the tasks are too different, or if the model can't figure out which parts of the knowledge to reuse, it can make things worse instead of better.
So, how do we make sure we get positive transfer and avoid negative transfer? Is there a magic formula?
There's no magic formula, Alice, but there are good practices. The key is to look for similarities between the source and target tasks. If they're similar, transfer learning is likely to help. If they're too different, you might need to rethink your approach.
Christy, can you give us a real-world example? Like, how does this actually work in code?
Sure thing. Let's say you want to build an image classifier for different types of cars. Instead of training a neural network from scratch, you can start with a pre-trained model like VGG16 or RaiseNet 50, which already knows how to recognize thousands of objects from ImageNet. You just swap out the last layer and retrain it on your car images. Boom! You get a working model in a fraction of the time.
That's so cool. So you're basically giving your model a head start by letting it reuse what it already knows.
Exactly, Alice. And it's not just for images. In natural language processing, you can take a pre-trained model like BERT or GPT-2 and fine-tune it for your specific task, like classifying customer feedback or generating chatbot responses.
Wait, Melanie, how does this actually help with resource usage? Like, does it save time and money?
Absolutely, Christy. Training deep learning models from scratch takes a ton of data and compute power. With transfer learning, you can get great results with much less data and much faster training because the model already knows how to extract useful features. It's like hiring an experienced chef instead of training a new one from scratch.
And it's not just about speed. Transfer learning can also help prevent overfitting because the model has already learned general features from a huge dataset. That means it's less likely to get too specialized and perform poorly on new data.
That's a huge win. But what about when things go wrong? Like, what if the pre-trained model was trained on cats and dogs, and now you want to recognize cars? Can that cause problems?
Great question, Christy. If the source and target domains are too different, you might get negative transfer, like we talked about earlier. But if there's at least some overlap, like both involve recognizing objects in images, transfer learning usually helps. The model just needs to adjust its thinking a bit for the new task.
And that's why we talk about fine-tuning instead of just using the pre-trained model as is. You keep most of the model's knowledge, but you tweak the last few layers to adapt to your specific problem.
Christy, can we talk about the history a bit more? Like, how did we get from psychology to machine learning?
Sure, the idea of transfer learning started in psychology around 1901, with Thorndike and Woodworth studying how skills in one area affect another. Then, in 1908, Judd argued that transfer is about abstracting general principles. So if you learn the underlying rules, you can apply them to new situations.
Right, and over the years, researchers kept refining the idea. In the 1950s, Polya talked about problem-solving strategies and how analogy helps us solve new problems. By the 1970s, people were talking about lateral transfer, using knowledge at the same level of complexity, but in a different context.
And in machine learning, transfer learning was explicitly mentioned in 1976 by Bozanovsky and Fulgosi, who talked about leveraging trained models on new tasks. Since then, it's become a cornerstone of modern AI, especially with the rise of deep learning and pre-trained models.
That's a long journey. So in practice, how do you decide when to use transfer learning?
Great question, Christy. You should consider transfer learning when you have a small dataset, limited compute resources, or when your task is similar to something a pre-trained model already knows. For example, if you want to build a medical image classifier but only have a few hundred images, transfer learning is your best friend.
And what about the opposite? When should you avoid it?
If your task is totally different from what the pre-trained model was trained on, like trying to use an image model for text data, transfer learning probably won't help. And sometimes, as we saw with some recent research, pre-training can even hurt performance if the domains are too dissimilar.
That's super important to keep in mind, so let's talk about some popular pre-trained models. Alice, you mentioned VGG and RaiseNet for images. What about NLP?
For NLP, BERT, GPT-2, and Elmo are the big names. BERT, for example, is pre-trained on a huge corpus of text and can be fine-tuned for tasks like question answering, sentiment analysis, or named entity recognition. GPT-2 is great for text generation, like writing stories or chatbot responses.
And what about speech recognition?
For speech, models like deep speech are pre-trained on large audio datasets and can be fine-tuned for new languages or accents. The idea is the same. Reuse what's already been learned to make training faster and more effective.
Christy, what's the biggest takeaway for developers who are just starting with transfer learning?
I'd say the biggest takeaway is that you don't have to start from scratch. There's a huge ecosystem of pre-trained models out there, and transfer learning lets you build on top of them. It's like standing on the shoulders of giants. You get better results, faster, and with less data.
And don't forget about the psychology behind it. Transfer learning is all about building on what's already known, whether you're a human or a machine. It's a powerful idea that's shaped both education and artificial intelligence.
Exactly, and as developers, we get to use these ideas to build smarter, more efficient models. It's one of the most exciting parts of modern machine learning.
So to wrap up, transfer learning is a bridge between psychology and machine learning. It's a huge time saver and it's making AI more accessible to everyone. Thanks everyone for such a lively discussion. All right, team, let's shake things up a bit. We've covered transfer learning, but now I want to talk about something that's really changing the game in Gen AI, retrieval augmented generation or RAG. Alice, Christy, Melanie, let's dig into how RAG is making AI smarter and more reliable.
Oh, RAG is such a hot topic right now. Mike, can I just say, this is the tech that finally lets AI give answers that are both creative and actually accurate. No more hallucinated birthdays for Janet from some random universe.
Wait, so RAG is like giving your AI a cheat sheet? Or is it more like letting it look up stuff in a library while it's answering questions?
Great analogy, Christy. It's both. Imagine you're taking an exam. You remember some things from years ago, your parametric memory, but for the tricky questions, you grab a textbook off the shelf. That's non-parametric memory. RAG combines both, the neural network's internal knowledge and real-time lookups from an external database.
So if I ask, what was on line 220 of Arthur's payslip in December 2020? A regular language model would just make something up, right? But RAG would actually go fetch the real payslip and answer with the correct amount.
Exactly, that's the magic. The retrieval system fetches the relevant document, and the generator crafts a fluent answer using that real data. It's like having a superpowered assistant who not only remembers a lot, but also double-checks facts before answering.
Let's break down the steps for developers, because this is where it gets cool. First, the user asks a question, like show me all server errors at 18:30 on April 20, 2022. The retriever encodes this query into a dense vector, which is basically a mathematical fingerprint of the question.
Hold on, Melanie, what's a dense vector? Is that like word embeddings?
Exactly, Christy. It's a way to represent the meaning of the query so the retriever can efficiently match it to relevant documents in the database. Think of it as mapping both questions and documents into the same idea space so you can find what's closest.
So after the query is turned into a vector, the retriever searches the database, like Pinecone or FAISS, and pulls out the most relevant documents. Then what?
Then the retriever encodes those documents into vectors too, so everything's speaking the same language. These documents are passed along to the generator, which is usually a big language model like GPT-3, BART, or T5.
And now the generator has both the question and the supporting documents. It uses all that context to write an answer that's both fluent and factually grounded. No more guessing or making things up.
And here's the kicker. The system can show you exactly which documents it used to generate the answer. So if you ask, "What's the capital of France?" and it says Paris, it'll also show you the Wikipedia article it pulled from. That's transparency.
That's so much better than the old black box models. But what kind of neural networks are used for the retriever part? Are we talking BERT again?
Absolutely. Some of the best retrievers are based on BERT and its relatives. For example, Colbert uses BERT for contextualized late interaction, ANCE uses approximate nearest neighbor search, and Realm actually pre-trains the retriever with the generator so they work together. TASB is another one, mixing sparse and dense retrieval for speed and accuracy.
And for the generator, it's the usual suspects: GPT-2, GPT-3, BART, T5. These models are amazing at generating text, but when you add RAG, they get a reality check from the retriever.
Let's make this super concrete. Say you're building a customer support bot. With RAG, when a user asks, "How do I reset my router?" the retriever grabs the latest manual or FAQ, and the generator crafts a step-by-step answer using that source. If the manual updates, your bot's answers update too, no retraining needed.
Wait, so RAG is like plugging your model into a live knowledge base. That means it always has the latest info, right?
Exactly. That's why RAG is so powerful for enterprise apps, legal research, and anything where accuracy and freshness matter. You're not limited to what the model saw during training. You can add new documents anytime.
But what about performance? Doesn't searching a huge database slow things down?
Great point, Mike. That's where vector databases like Pinecone or FAISS shine. They're optimized for lightning-fast similarity search, even with millions of documents. Plus, the retriever model is usually much smaller and faster than the generator.
And developers can tune the retriever to fetch more or fewer documents, depending on how much context the generator needs. You can balance speed and accuracy for your use case.
May I say something here?
Sure, Alice, please go ahead.
I love how RAG also helps with hallucinations. If the answer isn't in the database, the model can say, "Sorry, I couldn't find that information," instead of inventing something.
Exactly. It's a huge step forward for trust and reliability. And it's not just for text. RAG concepts are spreading to code generation, medical research, and even video Q&A.
So to sum up for developers, RAG is like giving your Gen AI a memory upgrade. It combines what the model knows with what it can look up in real time. You get answers that are creative, accurate, up-to-date, and transparent.
And the best part? You can mix and match retrievers and generators. Try Colbert with GPT-3 or Realm with T5. Experiment and see what works for your data.
Plus, you can keep your knowledge base private and secure. No need to send sensitive queries to a public API. Just point your retriever at your own database.
Honestly, RAG is the future of reliable, explainable AI. If you're a developer, this is the tech to watch and to start building with.
Couldn't agree more. Thanks everyone for making RAG sound as exciting as it really is. Stay tuned. Welcome back everyone. We've got that deep dive on RAG strategies today. Christy, as our AI researcher, can you kick us off with dense retrieval?
Absolutely, Mike. Dense retrieval is fascinating. It uses models like BERT or Facebook's DPR to encode queries and documents into dense vectors. The magic happens in the embedding space where semantic similarity is measured through cosine similarity. Perfect for when users ask about server issues, and we want logs mentioning latency, timeouts, or bottlenecks, even without exact keyword matches.
And the implementation is methodical. First, you choose a pre-trained model BERT, row BERTA, or DPR. Then you encode queries and documents into vectors. The document encoding can be computationally heavy upfront, but it's a one-time cost. Finally, you compute similarity scores and retrieve top K documents. The real power? It understands meaning beyond keywords.
But what about when precision matters?
That's where sparse retrieval shines. It's based on traditional IR methods like TF-IDF or BM25. Documents become sparse vectors weighted by term frequency and inverse document frequency. If you're searching legal contracts for every indemnification clause, this gives you exact matches fast. Simple, interpretable, and lightning quick for unambiguous terms.
Now combine them, and you get hybrid retrieval. This is where modern NLP meets traditional IR. You run both dense and sparse retrievals simultaneously, then merge the ranked lists or use one to re-rank the other. The dense retrieval captures semantic understanding, while sparse ensures precision. For medical diagnosis systems, this balance is crucial, understanding symptom descriptions while precisely matching drug names.
What about complex queries that need refinement?
That's iterative retrieval's domain. It's multi-round retrieval where each round informs the next. Start with what causes server crashes, get general docs, then refine to how does memory leakage cause crashes in Linux systems. By adding context from initial results, you can do 3-5 iterations, dynamically narrowing results. Perfect for research assistance.
And query expansion is like giving your search superpowers. It enhances initial queries by adding related terms through synonym expansion or knowledge bases. Search for AI expands to machine learning, neural networks, deep learning. E-commerce loves this. Laptop queries automatically include Notebook, Ultrabook, and Chromebook. Boosts recall dramatically.
Don't forget contextual retrieval. This considers the broader context, previous queries, surrounding text, or user history. When a user follows, "My router is broken," with lights are blinking red, the system maintains context without repetition. Chatbots using this feel eerily intelligent because they track conversation threads.
For precision answers, passage retrieval is revolutionary. Instead of full documents, it retrieves targeted passages. First segment documents into paragraphs or sentences, then encode passages separately. When users ask how to reset password, it fetches just the relevant steps, not the whole manual. Saves computation and reduces generator workload.
The most advanced is end-to-end retrieval and generation. Here, retrieval and generation happen simultaneously. The generator dynamically formulates queries as it writes. Imagine it generating. "The French Revolution began in..." Pauses, queries French Revolution start date, retrieves documents, then continues 1789. Like a journalist fact-checking mid-article.
So which strategy wins?
It's situational, Mike. Customer support, start with hybrid, add iterative refinement. Legal database, sparse for precision. Research assistant, dense with query expansion. Medical Q&A, passage retrieval for targeted answers. The beauty is mix and match like Lego blocks for AI.
Exactly. And with vector databases like FAISS handling million document searches in milliseconds, these strategies become practical.
I'm using iterative plus passage retrieval for my cat care FAQ bot. Why is Mittens vomiting? Leads to check hairball remedies, then recommended brands.
Brilliant. Remember, Team RAG strategies are your toolkit. Choose wisely based on use case, semantic understanding, dense, precision, sparse, complexity, iterative, brevity, passage. The future is contextual end-to-end systems.
Couldn't agree more. Developers experiment with these strategies. Try dense retrieval with GPT-4 or hybrid approaches with Colbert. Build amazing things.
And share your creations. This is how we advance the field together. Until next time. Hey Christy, I've been hearing a lot about generative adversarial networks, or GANs, and how they're behind deepfakes and AI-generated art. Can you walk me through what they are and how they got started?
Absolutely, Mike. So GANs first appeared in 2014, thanks to Ian Goodfellow. Legend has it he came up with the idea during a lively discussion at a bar near the University of Montreal. The core concept is clever. You have two neural networks competing against each other. One is called the generator, which tries to create fake data, like images, and the other is the discriminator, which tries to tell real data apart from fakes. Imagine an AI counterfeiter versus an AI investigator, both learning from each other.
That competition is kind of like what we see in nature.
What do you mean by that?
Think of Bayesian mimicry, where a harmless butterfly evolves to look like a poisonous one so predators avoid it. The generator is like that mimic trying to fool the discriminator. And when both networks improve together, like in Mullerian mimicry, where two toxic species evolve to look more similar for mutual benefit, that's like the minimax game in GAN training. Each side pushes the other to get better.
Exactly. But of course, the early years of GAN research were pretty chaotic.
Between 2014 and 2016, people called GANs the Wild West of AI. A lot of times, generators would get stuck in something called mode collapse, basically producing the same image over and over instead of learning diversity. The outputs were often very grainy, low resolution, 64 times 64 pixel images. It felt like we'd made a neat idea but didn't know how to stabilize it yet.
That changed in 2015 with DCGANs, deep convolutional GANs. They introduced convolutional layers and batch normalization, which brought much-needed stability and made the images a lot clearer.
Got it, so DCGANs were a big step forward. What happened next?
In 2016, we saw the rise of conditional GANs, or CGANs. Before that, GANs just learned to generate data without any guidance. With CGANs, you could feed in labels or text prompts. So if you wanted a tabby cat wearing sunglasses, the generator had a clear instruction. This concept paved the way for later text-to-image tools like DALL-E.
And soon after, researchers tackled image resolution. In 2017, progressive GANs came along. They started training on small images like 4 times 4 pixels and gradually added layers to reach much bigger sizes, ultimately producing 1024 times 1024 high-quality faces. Then in 2018, style GAN separated high-level attributes, like pose or hairstyle, from fine details like freckles or lighting, giving us a lot more control over generated images.
That's awesome, but for someone just diving in, I'd love to know how these different GAN flavors work under the hood. Could you break down a few popular architectures?
Sure thing, let's start with DCGAN. It uses transposed convolution layers in the generator to upsample noise into an image, and regular convolution layers in the discriminator to downsample images into a single real V's fake score. It's a solid foundation for beginners. Next up, WGANGP, Wasserstein GAN with gradient penalty, focuses on training stability. It replaces the original GAN loss with the Wasserstein distance and adds a gradient penalty term to keep the discriminator's gradients under control. This prevents mode collapse and gives smoother training curves, really important in fields like medical imaging, where you need diverse outputs.
Then there's SNGAN, Spectral Normalization GAN. It puts a training wheel on the discriminator by normalizing its weights, which keeps its gradients within a stable range. That also helps avoid crazy spikes in training and helps the model learn more reliably. And CGANPD, which stands for Conditional GAN with Projection Discriminator. It injects class information directly into the discriminator's layers, helping the network understand which label the image is supposed to belong to. This is especially useful in industrial settings. Think defect detection on an assembly line, where you need very clean, labeled, generated examples.
Don't forget self-supervised GANs, SSGANs, and Infomax GANs. SSGANs use auxiliary tasks, like predicting image rotations, to learn better feature representations. That's great when you have limited labeled data. Infomax GANs, on the other hand, use contrastive learning to fight mode collapse, ensuring that generated images remain diverse. For example, in dermatology, you might use Infomax GAN to produce a wide variety of melanoma images for training a classifier on rare cases.
This is making more sense. But once you've trained a GAN, how do you know if it's doing well? I've heard about inception score and FID. What are those?
The inception score measures both image quality and diversity. It runs generated images through a pre-trained inception model and looks at the predicted label distribution. If the images are sharp and clearly recognizable, they get a high score. If they're diverse across different labels, that also improves the score. Frachet inception distance, or FID, goes a step further. It compares the distribution of features from real images and generated images, again using a pre-trained inception network. Lower FID means the generated images distribution is closer to the real images distribution, which implies higher realism and diversity.
Still, many researchers say human evaluation is the gold standard. For example, you might run a study on Amazon Mechanical Turk asking people to spot which images are fake. If they can't tell, or only get it right half the time, that's a sign your generator is doing its job really well.
That makes sense. Cool. Now, let's say I am Melanie starting my first GAN project. What's a practical step-by-step I can follow?
Okay, Melanie, here's a straightforward outline. 1. Data preparation. Decide on your target resolution. Let's say 256 times 256 pixel images of pets. Gather and pre-process your dataset. Crop or resize images. Normalize pixel values to a range like -1, +1. 2. Build the generator. Start with a noise vector Z, e.g., 100 dimensional, sampled from a normal distribution. Use a series of transposed convolution layers to upsample Z into a 256 times 256 times 3 image. Apply batch normalization and Ray-LU activations on intermediate layers. Use a final tan activation so pixel values end up between -1 and +1. 3. Build the discriminator. Input is a 256 times 256 times 3 image. Use downsampling convolution layers, stride 2, kernel size 4, with leaky Ray-LU activations. Gradually reduce spatial dimensions until you have a single output neuron. Use a sigmoid activation at the end to predict real 1 or fake 0. 4. Adversarial training loop. Step A. Sample a batch of real images and a batch of random noise. Step B. Generate fake images with the generator. Step C. Compute discriminator loss on real images, label equals 1, and fake images, label equals 0. Backpropagate and update discriminator weights. Step D. Sample a new batch of noise, generate fake images, then compute generator loss by feeding those fakes through the discriminator, label equals 1. Backpropagate and update only the generator. You alternate between updating the discriminator and the generator. That's the Minimax game. Ideally, it converges when the discriminator can no longer reliably tell real from fake 50-50 accuracy, meaning the generator is fooling it.
And for reproducibility, I'll point you to Mimicry, a PyTorch library that standardizes GAN training. You can just pip install Mimicry, pick from DCGAN, WGAN-GP, SNGAN, and get built-in training loops. It even computes FID for you, so you're not stuck wondering if your results are comparable to someone else's. No more "my GPU made my GAN better" excuses.
Wow, this is really helpful, but we all know there are bigger issues. What about ethical concerns surrounding GANs?
Right, Mike. After 2018, deepfakes really blew up. People started making convincing fake videos of public figures. So now we have models specifically trained to detect GAN-generated media, an ongoing arms race. Every time detection improves, someone finds a new trick to generate more realistic fakes. Also, bias is a huge problem. Remember when style GAN2 models trained only on primarily Caucasian faces had trouble generating realistic faces of other ethnicities? If your training set isn't diverse, your GAN's outputs will be biased. It's absolutely critical to incorporate varied data to avoid perpetuating or amplifying societal biases.
On the flip side, GANs have mind-blowing positive applications. NVIDIA's Gauguin, for instance, can turn simple sketches into photorealistic landscapes, amazing for concept artists. In pharmaceuticals, researchers generate novel molecular structures for drug discovery. My team uses WGAN-GP to augment rare cancer histopathology images, which boosts our classifier's performance on underrepresented tumor types.
That's incredible, so GANs are helping save lives too. What does the future look like for this technology?
We're heading toward cross-modal GANs. Imagine generating a realistic MRI scan from just a textual medical report, or real-time video enhancement that outperforms traditional codecs. And researchers are already exploring hybrids that combine the best of GANs and diffusion models, trying to get the high fidelity of diffusion methods with the fast generation of GANs.
For aspiring developers, what would you recommend as a learning path?
Start small. Take PyTorch's DCGAN tutorial on the MNIST dataset. You'll generate 28 times 28-digit images in no time. Once you're comfortable, level up to something like Style GAN 3 if you're eager to make anime art or high-resolution human faces. Key tip: always maintain a balance between the generator and discriminator. If the discriminator becomes too strong too soon, the generator will struggle to learn.
And for hyperparameters, go with Atom Optimizer at a learning rate of 0.0002, beta 1 set to 0.5. Use a batch size between 64 and 128. If you need extra stability, apply spectral normalization to the discriminator's weights. Most importantly, visualize your outputs every epoch. There's no better feeling than watching your GAN gradually learn to draw.
Thanks everyone. Any final takeaways?
GANs teach us that an adversarial process, like competition in nature, can generate incredible creative power. Sure, training them can be finicky, but when it works, you open Pandora's box of generative potential. It's a wild ride, but the possibilities are endless.
Couldn't have said it better, thank you. So Christy, I keep hearing about stable diffusion. What exactly is it?
Stable diffusion is a type of deep generative model that creates images from text. Think of it as a smart painter guided by words.
How does it actually work under the hood?
At its core is a latent diffusion model, LDM. During training, it learns to add and remove noise in a lower dimensional space instead of full images. That makes it faster and more efficient.
Latent space, can you break that down, Alice?
Sure, instead of operating on huge pixel grids, the model compresses images into a compact latent representation using an autoencoder. Then it diffuses and denoises there.
So it's like sketching in pencil before coloring.
Exactly, rough ideas in latent, then final details in pixel space.
Melanie, what are the steps if I wanted to train one myself?
First, you define the diffusion process in latent space. Gradually add noise to encodings. Then train the network to reverse it, denoise, and reconstruct.
Isn't that slow? How do we generate new images?
For inference, you start with pure noise in the latent space, then run the learned denoising steps to shape it into an image. Finally, decode back to pixels.
Christy, why do people choose stable diffusion over older models?
Key advantages: efficiency and quality. Because it works in latent space, it uses less GPU and still outputs high-resolution images.
Any cool tricks for better control?
Yes, precision. You can tweak diffusion hyperparameters, like the number of denoising steps or strength of noise, to fine-tune details.
Melanie, how do I get started on my laptop?
Install a stable diffusion web UI, like Automatic 1111. Follow the repo instructions, ensure your GPU meets requirements, and launch the interface.
Does it run on CPU too?
You can, but it's painfully slow. GPU with at least 6 GB VRAM is recommended for 512 times 512 images.
Alice, any tips for writing prompts?
Keep them descriptive but concise. Mention style, lighting, subject. Example, a sunset over mountains in watercolor style.
And where do I find example images or assets?
Check out Pexels and the NYPL digital collections for free resources.
Wait, NYPL has images for AI training.
Yes, their public domain photos are great for artistic datasets.
Christy, I saw links to LAION5B. What's that?
LAION5B is a huge openly licensed dataset of image, text pairs that many stable diffusion models use for training.
Alice, how does Stable Diffusion compare to DALL-E?
They're similar conceptually, but Stable Diffusion is open source and runs locally. DALL-E is a proprietary service.
Melanie, any pitfalls I should watch out for?
Watch out for poor normalization or mismatched resolutions. Also, running out of VRAM mid-training can crash the process.
Christy, can Stable Diffusion do video?
Not directly, it's image-based. But you can generate frames sequentially or use ControlNet extensions for motion consistency.
ControlNet, tell me more.
It's a module that conditions diffusion on extra inputs, like edge maps or pose sketches, so you get better structure in generated images.
Any final pro tips?
Tune your denoising schedule. More steps equals finer detail but slower speed. Also, experiment with different text encoders for style variation.
Mike, any final thoughts on Stable Diffusion?
Honestly, I'm blown away running this on a consumer laptop, and turning a simple text prompt into a detailed, photorealistic image feels like magic. The blend of efficiency and creative control is unparalleled, and I can't wait to experiment with LoRa, ControlNet, and custom prompts to see where it takes my projects next. We've been diving deep into neural networks and all these fancy techniques, but at the end of the day, don't we need a way to actually test if they're giving us the right answers? How do we know if the LLM's answer is actually correct?
A key technique is computing a confidence score for each response.
Confidence score, how would that work in practice?
Think hybrid search augmented generation. We retrieve relevant documents using FAIS and BM25, then use those similarity scores.
Wait, so we run two searches, one with FAIS, one with BM25, and compare.
Exactly. FAIS gives us vector similarities, BM25 gives term-based scores. We take the top K matches from each and compute how well they align with the query.
Can you please break down the steps without getting too code heavy?
Sure, first, encode the user's question into a vector, usually with the same encoder used to build the FAIS index.
Then perform a FAIS search to get the top K nearest neighbors in latent space. Right.
Correct, we calculate cosine similarity between the query vector and each candidate's vector.
And for BM25, we tokenize the query, transform tokens into an internal BM25 structure, then score documents based on term frequency and inverse document frequency.
Exactly, BM25 gives a relevant score for each document. We pick the top K documents there as well.
Once we have those two sets of top results, how do we merge the confidence scores?
Calculate the average similarity from FAIS for its top K and the average BM25 score for its own top K. Then you can simply average those two numbers, or weight them, to get a final confidence.
Is there a typical threshold you recommend? Like, when should we trust the answer?
It depends. For fact retrieval, maybe require BM25 AVG greater or equal to 0.22. For more nuanced summaries, set FAIS AVG greater or equal to 0.5. If both meet their thresholds, you're golden.
What happens if the confidence is below threshold?
The system could prompt the LLM to regenerate the answer or return a fallback like, "I'm not confident enough to answer."
Could we automate that retry logic in the notebook?
Absolutely. After computing global confidence, add a conditional. If confidence is less than threshold, call the LLM again or flag for human review.
In the sample code, is there a function that encapsulates all of this?
Yes, there's a calculate confidence function. It takes query and top K, then runs. 1. Query vector initialization. 2. FAIS similarity search. 3. Compute FAIS similarities. 4. Query preprocessing for BM25. 5. BM25 scores and top K retrieval. 6. Compute BM25 similarities. 7. Average both confidences and return.
Sounds neat. Any pitfalls to watch out for?
One issue is mismatched scoring scales. FAIS cosine scores range between 0 and 1, BM25 can be higher, You might normalize BM25 scores before averaging.
Good point. Also, what about very short queries? Does BM25 struggle there?
Short queries can yield sparse term matches. BM25 scores might be low. In that case, FAIS, which relies on semantic embeddings, can help fill gaps.
How would I choose top K 10, 20?
10 is a common default. But if your corpus is huge or you need more context, you might bump up to 20 or 30. Just measure latency.
Does the notebook show the code for building the FAIS index?
Yes, you load document embeddings, initialize a FAIS index, often index flat L2 or HNSW, and add all vectors. Then persist it to disk for fast lookups.
And for BM25, do we use an existing library?
Usually, the code wraps a library like rank BM25 or uses Pysarini. You take tokenized documents, build the BM25 index, and then query with tokenized input.
Nice. And normalizing BM25, would that be dividing by the maximum BM25 score in the batch?
One way, or scale into 0, 1 via min-max within your corpus stats.
How do we interpret the final confidence value? Is 0.6 good?
Depends on your threshold. If you set 0.5 for summaries and both components exceed their minima, 0.6 is acceptable. If you need high precision, aim for 0.8 plus.
What about real-world examples? Any benchmarks?
In one project, we set BM25 threshold at 0.22 and FAIS at 0.5. That gave 85% accuracy on fact-checking queries in our domain.
If confidence is low, how do we log or surface that to users?
You could append a disclaimer. Confidence, 0.35, please verify. Or route low confidence queries to a human operator.
Is it possible to weight BM25 and FAIS differently?
Yes, for example, final confidence equals 0.7 AVG FAIS plus 0.3 normalized BM25, if you trust semantic matches more.
Can this approach extend to non-text data?
Sure, if you embed images or audio. Use FAIS on embeddings and a classical retrieval method like inverted index for metadata. Then average those confidences.
Any tips for debugging low-confidence cases?
Inspect the top retrieved documents. If they're irrelevant, your embedding or BM25 vocabulary might need tweaking. Also check tokenization errors.
All right, time for a quick summary. Confidence scores rely on averaging FAIS and BM25 similarities from top K results, with optional normalization or weighted averaging. If below a threshold, regenerate or flag. Key is balancing semantic and lexical retrieval. That's concise, thank you. I feel more confident already. Hold on to your seats, because we're blasting off into the electrifying world of agentic AI. Think of it as turning language models into their own little superheroes.
I love that metaphor. Agentic AI basically fuses reinforcement learning vibes with LLM smarts, so these agents can literally think, plan, and take action, like AI with a brain and a backbone.
So instead of slogging through millions of trial and error loops with reward functions, these agents use chain of thought prompts to spark their reasoning. That sounds way more fun.
Exactly, it's like giving them a cheat code. COTI or chain of thought methods help LLMs generalize from just a handful of examples, so heavy RL training feels almost optional.
I'm wondering, how did we go from simple chain of thought to these full-blown agentic systems? It's amazing how fast it's evolving.
Picture this. Back in 2022, we started with basic chain of thought prompts like, let's break this down step by step. That was the seed of it all. Right, and then came program of thoughts, or POTI, where we combined pseudo-code logic with natural language. Its prompt sounded like this: combine natural language reasoning and programming logic to solve this problem. Start by writing pseudocode or logic reasoning steps to describe your approach.
Oh, and Table of Thoughts or Tab COTI arrived with its prompt sounding like this. Create a table where each row corresponds to a subproblem. Define the columns as step, sub-question, process, and result. Use it to model the reasoning process. Haha, I did too. Then tree of thoughts or TT popped up. Its prompt sounded like this. Develop a tree of potential solutions where each node represents a decision point or reasoning step. Consider alternative paths and backtrack if necessary. Present the initial branches.
I can't forget recursive enhancements prompting the model to tackle nested sub-problems with those nifty think-geo stop tokens. Its prompt went like this: utilize recursion to handle nested sub-problems. Begin with the primary problem, break it into smaller contexts, and solve each recursively using think-geo stop tokens for clarity. It felt like teaching a kid to solve puzzles. And automate chain of thought or COTI example. Generate multiple potential reasoning paths. Use heuristics to prune inconsistent ones and optimize the selection of the final reasoning chain using variance reduction or policy gradients.
By 2023, Agent Bench and Chain of Action let us run dynamic performance tests, kind of like pit two AIs against each other in reasoning boxing. Sample prompt for it sounded like this: design a sequence of actions as a chain of thoughts, intended to solve a task by integrating reasoning at each step. Use Agent Bench for benchmarking performance dynamically. In 2024, agent integration became known with prompts like integrate reasoning with actions in an agentic framework. Allow the agent to perceive, decide, and interact using LLMs to bridge the gap between thought and observation.
Also in 2024, Graph of Thoughts Rationale or GOTI Rationale came up. It prompt sounds like this: model your thought process as a graph, generate the pathway of thoughts, and use rationale to verify and score them dynamically. Start with creating the basic nodes of this graph.
So is it true that all these advances melt into one supercharged agentic AI system?
Exactly. It taps into pre-trained LLM knowledge, sprinkles in RL-like policies, and voila, agents that can plan, reason, and act in a continuous loop.
How does this vibe compare to classic RL agents that learn purely from reward functions? I tried teaching one to play a game once, never-ending loops.
Classic RL is like sending an agent into a maze blindfolded, hit the walls to learn. Agentic AI with prompts guiding it is more like handing the agent a map and compass, much quicker learning.
I feel that. With RL, you need tons of trials. With prompts, you just nudge the agent in the right direction from the get-go.
What about multi-agent setups? I heard there's a bird's-eye view of how they kick off and run together.
Imagine assigning each agent a role, like detective, planner, executor, and embedding COTI strategies in their prompt templates. They sense inputs, interacting dynamically on them with COTI, then coordinate actions in a loop.
That perceive, reason, act cycle, it's like watching a team of AI players improvise on stage, each taking cues from the others.
Exactly. They can ping external tools, update their beliefs, and refine next moves using action chains or reasoning graphs, like a jazz band interacting dynamically with each other.
Why is agentic AI so dang exciting for real-world stuff? I mean, I get the hype, but lay it on me.
Picture complex reasoning, like crisis management or financial planning, handled autonomously. Agents can strategize on the fly, pivot when new data drops, and execute without a human in the loop.
And because we're using LLM prompts instead of training from scratch, you deploy these agents ridiculously fast with total transparency. No black box drama.
Plus, when you fold in RL-style exploration versus exploitation, agents can still chase rewards when needed. So they're not just talk, they walk the walk.
In a nutshell, agentic AI hands us autonomous linguistic agents that think like us and act in the world. Prompt-driven, RL-empowered, and downright next level.
I'm giddy just thinking about the possibilities. Agentic AI is rewriting the playbook for smart, adaptive systems. Friends, finally and lastly, we are going to discuss and dive into the fascinating world of AI ops, artificial intelligence for IT operations. So buckle up for an in-depth exploration of how AI is transforming the way we manage complex IT environments.
I'm excited. AI ops has been everywhere lately. But first, let's clarify what AI ops actually means and why it's so crucial right now.
Absolutely. At its core, AI Ops combines AI and machine learning to automate and enhance IT operations processes. Think anomaly detection, event correlation, root cause analysis, and incident management, using intelligent algorithms instead of manual workflows.
That's a lot to unpack. When we say anomaly detection in AI ops, what exactly happens behind the scenes?
Great question. Anomaly detection uses ML models to identify unusual patterns in system metrics or logs, anything that deviates from normal behavior. Tools like Dynatrace, Splunk, and Datadog ingest streams of data. Then algorithms such as statistical models or neural networks flag spikes, dips, or irregular patterns that could signal an impending issue.
Once an anomaly is flagged, how do we prevent alert storms? I've seen teams get overwhelmed by hundreds of alerts at once.
That's where event correlation comes in. AI ops platforms aggregate thousands of individual events, alerts from different monitoring tools, and use correlation algorithms to link related events. So instead of 50 separate alerts for CPU spikes, network latency, and failed logins, the system identifies that these are connected and surfaces a single correlated incident.
Right and Datadog is known for its event correlation capabilities, grouping events so operators can focus on what really matters.
Once events are correlated, the next step is root cause analysis. How do AI ops platforms actually pinpoint the underlying issue?
Root cause analysis, RCA, in AI ops involves ingesting large volumes of data, from metrics, logs, traces, configuration changes, to topological information, and applying AI algorithms, such as Bayesian models, graph-based analysis, or pattern mining, to trace back from symptoms to the actual fault. For example, Dynatrace uses causal AI to automatically map dependencies and locate the source of a slowdown or error.
That sounds incredibly powerful. And I assume once RCA is done, we move to incident management. How is that automated in an AI ops context?
Exactly. Automated incident management kicks in by leveraging tools like IBM Watson AI Ops and PagerDuty. Once an issue is detected and its root cause identified, these tools can automatically create, assign, and prioritize tickets, or even trigger runbooks to remediate problems. AI-driven deduplication ensures that similar incidents aren't reopened repeatedly.
So AI ops shifts it from reactive firefighting, where humans scramble to respond, to proactive problem solving. That's a game changer.
Exactly. By predicting and identifying issues before they escalate, you reduce downtime, optimize resource utilization, and cut operational costs. Gartner defines AI ops platforms as tools that enhance or replace core IT operations functions, advocating for a cultural shift toward automated, data-driven operations.
What sets AI ops apart from traditional IT management tools? I mean, we've had monitoring dashboards for years.
The key differentiators are observability, automation, and predictive intelligence. Observability means having a unified end-to-end view of the entire IT ecosystem, from applications and servers to network devices. AI ops platforms ingest metrics, logs, traces, and events into a data lakehouse, enabling real-time visibility.
And automation means routine tasks, alert triage, ticket creation, even initial remediation steps are handled by AI rather than humans.
Predictive information is also huge. By analyzing historical patterns with ML models, AI ops can forecast capacity constraints or potential failures, so teams can act before users even notice a problem.
Let's walk through the AI ops data flow, how data moves from source to action. Melanie, can you break it down?
Certainly, step one is data collection and ingestion. We deploy lightweight agents like Telegraph, Beats, or Fluented on servers and applications. Telegraph might gather CPU, memory, and application metrics. Beats handles log shipping into Elasticsearch. Fluented collects event data and routes it to a central store, be it files, databases, or streaming pipelines. This continuous ingestion ensures we capture every relevant data point.
Once the data's in, we need robust storage and management. What do you mean by a data lakehouse approach?
In a lakehouse, you combine the best of data lakes and data warehouses. You store raw, unstructured data, logs, metrics, traces, while also indexing and structuring it for analytics. Elasticsearch indexes text logs for fast search. InfluxDB handles time series metrics for high-velocity writes. ClickHouse, a columnar OLAP database, supports large-scale analytics queries. Together, they form a scalable, query-optimized architecture.
With data stored, the next phase is AI processing and behavioral analysis. What tools are involved here?
We use Apache NiFi or Spark to orchestrate data pipelines, ingesting, transforming, and feeding data into ML models. For incident prediction, you might employ Bayesian models, convolutional neural networks, CNNs, for pattern recognition, or recurrent neural networks, RNNs, to detect temporal anomalies. For root cause analysis, graph models can map dependencies, Markov models capture state transitions, and pattern mining finds recurring failure signatures.
Are there specific examples of these ML techniques in AI ops? I'd like a concrete illustration.
Sure, imagine using an RNN over event sequences to predict a cascading failure in a microservices architecture. The RNN learns that specific error patterns in service A often precede latency spikes in service B. It raises an alert before user experience tanks. For RCA, a graph neural network examines a dependency graph, database node, API layer, load balancer, to pinpoint that a misconfiguration in the load balancer caused downstream timeouts.
Once we've processed data, we need to visualize and monitor results. Which tools shine here?
Grafana is the go-to for time series dashboards, plotting CPU trends, error rates, request latencies. Kibana interfaces with Elasticsearch for log exploration and visual analysis. Metabase offers user-friendly dashboards for ad hoc queries. These visualization layers let operators quickly spot anomalies, drill down into metrics, and refine their alerts or ML models based on real-time feedback.
After we've detected incidents, visualized them, and correlated events, the final piece is automated incident management. Christy, how does AI decide what to do next?
Automated incident management triggers runbooks or remediation playbooks based on predefined rules or AI recommendations. For instance, IBM Watson AI Ops ingests the RCA output and can automatically restart a faulty microservice, roll back a problematic deployment, or scale up resources. PagerDuty can escalate critical incidents to on-call engineers, create tickets in Jira or ServiceNow, and even predict incident SLA breaches.
That's super efficient, but we still need humans to supervise, right? How does human interaction fit into this AI pipeline?
Absolutely, the last mile is human interpretation. Tools like ServiceNow integrate ticketing workflows so that when an AI flags a low confidence or high risk incident, it routes to an engineer. Splunk's ML toolkit can generate human readable reports summarizing AI findings. This collaboration ensures AI recommendations are validated and engineers can provide feedback to refine models, closing the loop.
I appreciate that we're not handing over the keys entirely to AI. Humans still make the final call on complex or ambiguous incidents.
Exactly. It's about augmenting human expertise, not replacing it. Also, interpretability is key. Even if a neural network model yields higher performance, an interpretable model, like a decision tree or rule-based system, may be preferred so engineers understand why an alert fired. This aligns with explainable AI, XAI principles.
Let's touch on the evolution and adoption of AI ops. How did we get from manual ops to this intelligent automation?
Initially, IT teams relied on siloed monitoring tools, one for logs, another for metrics, yet another for traces, each with separate dashboards. As infrastructures grew more complex, that approach became unsustainable. So in the early 2010s, vendors began integrating data and offering rule-based alerting. By the late 2010s, the explosion of big data and advances in ML made it feasible to apply AI, giving birth to AI ops.
Adoption has surged across industries. Financial services, retail, healthcare, anywhere uptime is critical. Organizations are also embracing site reliability engineering, SRE, practices alongside AI ops, using AI to shift left detection and resolution closer to the dev cycle.
What are some tangible benefits companies are seeing?
Companies report up to 60% faster incident resolution times, 30% reduction in false positive alerts, and significant cost savings by avoiding unplanned downtime. AI ops also frees up engineers to focus on strategic projects instead of constant firefighting.
Before we wrap, let's recap the core pillars of AI ops so our audience walks away with a clear framework.
First pillar, data ingestion and observability. Without comprehensive telemetry, logs, metrics, events, you can't build a reliable AI ops system.
Second pillar, AI-driven analytics. That includes anomaly detection, event correlation, RCA, predictive models, anything that leverages ML or statistical techniques to surface insights.
Third pillar, automation and orchestration. Use AI outputs to automate ticketing, runbook execution, scaling decisions, and remediation steps.
Fourth pillar, visualization and human collaboration. Dashboards, alerts, and integration with ticketing tools ensure that AI findings translate into actionable workflows.
Finally, interpretability and continuous feedback. Models must be explainable, and human input should feed back to improve AI performance over time.
Mike here, this has been an enlightening deep dive into AI ops. To sum up, by unifying and analyzing vast amounts of IT data, applying intelligent algorithms, and automating responses, AI ops empowers teams to anticipate problems, respond rapidly, and keep systems running smoothly. It's not just a tool set, it's a cultural shift toward data-driven, proactive operations. If you're new to AI ops, start by evaluating your existing monitoring landscape. Consolidate data sources, experiment with an open-source ML framework, and gradually build out anomaly detection pipelines. For seasoned pros, focus on integrating AI insights with your incident response processes and invest in making models interpretable. Thanks for joining us. Here's to smarter, more resilient IT operations with AI ops. Stay curious and happy automating.